Now, how many of you have done course survey evaluations? Online. Online evaluations. Awesome, thank you.
You're welcome.
That's worth 5 bonus points to you right there. Yes. You got it. You got 5 bonus points for being the only person paying attention. You've done it too? Oh, God, now your hand comes up. Oh, yeah, the hands are coming up all over now. All right, let me see who's really done it.
I can show it to you.
I'll do it right now.
Yes.
I did the pre-calls work.
Yeah, didn't you say we were gonna do it?
No, I said I didn't want to do it in class, but I was going to penalize you and take you up there like a bunch of kindergarten students, make you walk in a line and by height and what? By height.
My first.
No, you're last. Tallest always last. Actually, tallest is at the ends, and then it goes down. You get the perception of equal height.
You look bell curve.
Yeah, it's sort of like an inverse bell curve. I've got some experience in this area. So anyway, do it, all right? I'm just joshing about that.
Seriously? What?
Oh, man, Austin, you don't need 5 points.
Are you? Did you see my grade?
Well, all right, I'll keep it in mind if at the very end you need 5 points, okay?
Okay, I like that.
All right,
I like
yeah,
that.
all right, let's go. We got a lot to do today. Did Louis show up? We pass that back to him? Here's your homework. Let's go. It's the last class of any, this is the last class of new material. Okay? No, I would never say that. And we're going to spend all day on Wednesday going over this homework. Okay, so radiation exchange. Among many opaque, isothermal, diffuse gray surfaces. Now, I almost didn't teach this today and just focused on the homework because you don't really need this to solve the homework that I gave you. You can solve this just by making substitutions. But I thought I want to do it anyway. All right, because it's kind of important you understand how that this can be done. All right, let's say we have a surface I. And we'll call that, of course, that would be EBI. And this would be some QI that would be leading and being sent out to multiple surfaces. And all right, where this would be J1, J2, J3, all the way down to Jn. Okay? And this would then be 1 over AIF I to 1 over AIF I to 2, 1 over AIF I to 3, and this would be 1 over AIF I to N. And there would be appropriate heat transfers from each one of these. This would be Q I to 1, Q I to 2, Q I to 3, and Q I to N. And it doesn't matter how many you have, you just do it like this. So the this would represent the heat transfer from one surface area AI to all others. Okay, so that would be, I mean, many real-life examples you have to do something like this. Although, there are different ways to skin this cat. So let's go ahead and take a look at the first law. So what we have here is that Qi is going to be equal to the summation from I equals 1, oh, excuse me, Qi is going to be equal to the summation from j equals 1 n of Qi to j. So in other words, summing this one, this one, this one, and so forth, including the final one. Fair enough? You'd agree with that? That's what comes into this node has to equal what leaves the node. Okay? So what comes into the node equals what leaves the node. And we can write that out, and it's going to look like this. Qi is going to be EBI minus JI over 1 minus epsilon I over epsilon I AI. And that's going to be equal to the summation from j equals 1 to n of JI minus JJ over 1 over AIFI to j. And this is equation 1321. And you could write that equation for however many surfaces you have. Let's go ahead now and do a little expansion, which is interesting. The first thing we're going to do, okay, up here, first thing we're going to do is we're going to cancel these out. AI is in the denominator of every term. So we can just cancel that out. Simplify. Then we're going to say, we're going to multiply this side by top and bottom by epsilon sub I. So we'll have epsilon sub I times EBI minus JI over 1 minus epsilon I. And that's going to equal the summation from j equals 1 to n of JI minus JJ times Fij, where we simply multiply both numerator and denominator of Fij in each term. All right, and that's going to be equal to Ji, because we're going to bring the Ji's out, times the sum of J, times the summation from J equals 1 to n of Fij. Now what is this term?
Summation of the factors.
All the 2 factors.
One.
What is it? What?
1.
Thank you, John. Exactly. That term is equal to 1, so we're left just with Ji, and then we have minus the summation from j equals 1 to n of Jj times Fij. Okay? Now it gets more interesting. All right, so then following on, we have epsilon I times E B I minus Ji times, and now we're going to multiply both left and right sides by 1 minus epsilon I. It's going to be equal to 1 minus epsilon I times Ji minus 1 minus epsilon I times the summation from j equals 1 to n of fj fij. And we're going to then expand like so. Yeah. There. Okay. I carried away with my F's. That's the J's. All right. So what happens is this cancels this. All right. So Ji then will be equal to epsilon I E B I plus 1 minus epsilon I times the summation of j equals 1 to n of j j f I j. And you can solve this when the temperatures are known. So how do you do that? We use a matrix solution. Exactly like we did before. For series of linear equations. What you do is you construct a similar equation for every node, for every surface. Okay? And you solve for all the constants. And then you construct your matrices. Where A will be equal to all the constants JJ's. C will be your constants otherwise. And you'll get your constants values from these, from this term right here. Because this will be sigma t to the fourth of sigma times epsilon I times sigma ti to the fourth.
Is it common that you know the emissivity like that?
Well, you're going to have to know something. You're going to have to know the temperatures if you're going to solve for the J's. Yeah. And would you know the emissivities? You're going to make a good guess up. Okay. In the back of the book, there's a whole tables of emissivity. And if you go to big, I mean, this is undergraduate heat transfer book. If you go to a radiation book, there's lots and lots of data. Emissivities are related to temperature. And then J will be equal to your J sub J values. So you form the three matrices, then this should look very familiar to you. A times J equal to C, and you are going to invert and multiply. To solve for the J's, the J's will then be equal to A, the A matrix inverted times C, and you'll solve for your J values. There is an alternative solution. You can iterate. Certainly, probably would not want to do that. Question for you. What if the heat transfers are given? Heat transfer terms Qi are given. And the temperatures are unknown. You can solve it still, just working the other way. In this case, Qi double prime would be equal to Qi divided by Ai, which would be equal to EBi minus Ji over 1 minus epsilon I over epsilon. And then Qi will be equal to the summation from J equals 1 to N of Ji minus Jj over 1 minus Ai 1 over Ai F I and J. Or Ji will be equal to Qi prime plus summation from J equals 1 to N of J F I J, and you do the same sort of matrix formation and solve for the J's then, if the Q's are known. All right. Now the good news is you're not going to have to do this, but I wanted to show you how you could do this. What you do have to do on the homework, which I gave you on Friday, is you have to write out these equations, the nodal equations. But you have 4 surfaces in play. But because some of these surfaces are large or re-radiating, they simplify and you're able to solve directly. Okay? We'll talk about that next time's class. But for right now, let's take the homework assignment that I gave you last time, and let's answer any questions you have on that. I said, come to class having worked through part question C. All right. Okay, so. The first thing you have to do is to do the heating panel. You have to calculate the free convection from the panel. Now, the panel is hot surface up, right? Okay, so you've got hot surface up. Now, you've got a little bit of an issue. And how are you going to deal with this issue is the question. Okay, and what is the issue? Pardon me? What is going to be
Calculating the.
your characteristic length? Yeah, go ahead.
Never mind.
The area over the perimeter?
W over 2.
Yeah, except we don't give you a length into the,
Use
We
the
don't
per
give-
unit length, but-
yeah, I get- that would be the way that I solve it. It's not a perfect thing, so what would that be? What is the width?
0.5.
All right, so if the width is 0.5, and then you'd have
Times the length of 1,
1,
then divide by a perimeter of 0.5 times 2 plus 1 times 2.
and you, what do you get?
1/6.
1/6. All right, so looking for the characteristic length. All right. What does it say, though? Well, it says a long rod heater. Okay? A long rod heater. If it was long, let's just say it was 5 meters long. Okay? What would the characteristic length be?
Now we're talking about the rod, not the panel.
It's all the same, it's all one assembly. Okay, so the panel's long, the rod's long, what if it were 5 meters long? Pardon me?
5?
Well, then it'd be 5, 5, and 1, it'd be 11, divided by what? So then it'd be 5 times 1, or 5,
Be 5 times point.
the area divided by the perimeter. What would the area be if it were 5 meters long?
Is this the one for the diameter? That's
5 times, oh yeah, 2.5 divided by the perimeter, which would be
5.
perimeter. 11, right? 12. No, 11. So what would that be? Okay.
We're approaching a half. Okay?
Are we approaching a half?
Yeah, we are.
No, we're not.
No?
No, we're already less than half. What are we approaching? What if it was 10? Then it'd be 5 divided by 20, 21.
Oh, we're approaching a quarter.
We're approaching a quarter. And that's the way you gotta look at these things. When it says long, you can't, okay? So, is equal to what? Well, it's long. And for long, L sub C is going to be equal to, let's see, where am I here? Where am I? Long is going to equal approach, the width divided by 2. All right? So the characteristic length is going to be 0.25 meters.
No,
Pardon me?
no, what you just said, 0.5.
Well, that's what it approaches for a long panel, or for long. Okay? Go What's the matter?
I did this and then I erased it.
Okay, all right. So that's the first one. Then what equation are you going to use? Equation what? 931. Okay? And 931 is going to be okay, what's the Rayleigh number? Who's got it? Calculated with the new characteristic length. Yes?
I got a 6
70
point.
point. So,
I'm hearing some right ones, but
I got 70 times 10 to the 6th.
okay.
Yeah,
7 times 10
I got 6.97 times 10 to 7.
So it is
70 times 10 to 6 is otherwise known as 7.
Yeah.
I know 10 is 7. All right. Okay. All right, so you're going to solve for H3. What property, what temperature you going to take your properties?
350.
And TF is going to be what, 350? Okay, so who's got a value for H?
7.4.
H3. Go ahead.
7.4.
Okay. From there, it should be pretty straightforward. Now, what are you going to solve for? You're going to solve the heat transfer for what? How long?
25? No.
1 meter, just per unit. You're just going to do it per unit meter. Okay? All right. I won't give you that answer, but you should be able to get that pretty easily. So that's the first part. All right. Now you got to calculate the panel's radiosity J3. All right? Calculate the panel's radiosity J3. Recognize that the convective heat loss from the constant temperature plate is equal to the heat transfer, because the plate is constant temperature, is equal to the heat transfer associated with the surface radiative resistance. Okay? And why is that?
Heat in has to equal to heat out for constant temperature.
Yeah, the panel is very long.
It's insulated on the bottom side.
That's right, thank you. It's insulated, so it's got to be constant temperature, and what strikes it has got to leave, okay? Minus what is absorbed, and that's going to have to leave too, and how's that going to leave?
Convection.
Through convection, okay? So, if we do that, we have Q convection for surface 3 is going to be equal to EB3 minus J3 over 1 minus epsilon 3 over epsilon 3 A3. If we, go ahead, question?
Yeah, in the hint you have it backwards. You have J3 minus E3.
Oh, yeah. That's what I have written down.
Yeah, it doesn't really matter. It's just going to be the, it could go either way. Because it's just going to be sine,
Okay.
okay? Its convection is going to be out. So, we know the convection is out, right? So, I'll write it the way I have it on the thing. But what would this give you?
1637.
No, it'd give you a negative number, okay? If we solved it that way, it'd give you a negative number. This is just simply recognizing, by rearranging it in this fashion, it is simply recognizing that it's going to be out. All right, so then J3 will be equal to Q convection 3 times 1 minus epsilon 3 over epsilon 3 A3
Oh,
plus EB3. Okay? And what's this?
sigma T3 to the 4th.
What?
Sigma T3 to the 4th.
Okay? You know epsilon 3? You know A3?
Yeah,
Do you know the convection?
yeah, I'm gonna solve for
Can you solve for J3?
it. Yeah.
Sure.
What are the units on that?
On J3, watts per meter squared Kelvin.
That's what I noticed.
No.
Just watts per meter squared, excuse me, because you're going to multiply through by the Kelvin. All right? Pretty easy to solve for this. Yes, Patrick?
So how do we know QM?
You just solve for it.
Just solve for it right over here.
Oh,
Okay? Q of convection 3, can't write. Q convection 3 is going to be equal to H3 times A3 times T3 minus T of the surroundings. Okay? Yes, Louis?
So for A3, you just use 1 meter squared?
That's correct. For this dimension, we had to figure out what long meant, okay, in the limit. Down here, though, we're going to do all of our calculations for just 1 meter's worth of panel. So everything will be in terms of that first meter, okay? Are any questions so far? All right. Alrighty, so now that's pretty simple. Now let's get into things that are a little more difficult. View factors. Okay. All right, so how does surface 1 see things? Surface 1, make sure, surface 1 is our heater. All right. And our heater is right here. And then down below is our panel. And what happens is, this thing heats up and radiates, and then all this radiation is reflected back down on the panel. And these parabolic panels have that purpose. Now, the width from here to here is the same as from here to here. Okay? This is surface 3. This is surface 1. This is surface 2. And everything else is surface 4. Okay? And we know some dimensions here. We know the height. We know the width. We know the diameter. And we have to find all the shape factors, right? All right, so if we draw a line right here, we intersect the line connecting the two ends of the reflector plate, bisect the heating rod. So let's deal with how that rod sees surface 2. So who can explain to me what is F1 to 2?
0.5.
Why maybe?
Because the top half of the pipe sees the reflector exclusively, and it's only half of the pipe, so it's 0.5 instead of 1.
Right, and the bottom half of the pipe doesn't see it. Okay? Now the bottom half of the pipe sees what?
It sees the ground and the surface.
Sees the surroundings and the panel that we're heating, but it doesn't see anything else, okay? So if we want to do that, we could say F1 to 2 plus F2, F1 to 1 plus F1 to 2 plus F1 to 3 plus F1 to 4 equals 1. This is 0, doesn't see itself. This is 0.5, and we don't know how it sees 3 or 4. That's part of what we have to figure out. But at least we have this one. All right.
There's a formula in the textbook for 1 to 3.
Say what?
There's a formula for 1 to 3.
But he also told us how to do 1 to 3.
I did tell you how to do 1 to 3. All right. So let's look at this. 1 to 3. If we make the assumption that we can
All right, it's perpendicular.
draw this as a point, okay, which is not too far off, then this angle is equal to theta. Okay? We'll call that equal to theta. This is a point which sees a certain amount of the, what's the number of degrees from here to here? 180. So it sees a certain amount, although we have to consider the whole viewing, so it'd be 360 degrees. So what we're seeing is, of the complete circle that it sees, this pipe sees, it sees a certain percentage. And what do we know? We know the angle, and you say, well, how do you know the angle? How do you know the angle?
Like tangent.
Yes. We'll give you the, I'll share the equation with you in a moment. And then what is this?
5.
No, but what is it?
S.
What is it represented in this equation? Geometry.
2 times the opposite side.
How much of the circle?
Arc length.
Oh.
It's the arc length. Okay? It is the arc length. So we know the angle and we know the arc length. Okay? And what is, okay? So, the equation for that,
2 tangent inverse.
okay, right. Theta is equal to 2 times the
Inverse tangent.
inverse tangent of W over 2 over 2H, or
Why is it 2?
that's the equation that I have.
I just did.
Why 2H?
Yeah, shouldn't it just be H?
No,
Why?
Why?
well, trying to think.
Because if you do that, the tangent equals opposite over adjacent, correct? So Katoa,
Let's go with, hang on a second, what did you get for the argument of the tangent?
53 degrees.
Yeah.
That's what I got.
Oh, then maybe I have a mistake in here. So you got 53 with just H?
Yeah.
Okay, then maybe it could be,
I did 2.
oh, this is where,
Oh, you just slid it down?
yeah,
Okay.
I slid it down. Okay. And that is equal to
Sliding down.
53.13 degrees.
Don't you need it in radians?
No? No?
You divide by
Well,
360.
because what are you trying to do? Keep in mind what you're trying to do.
Get a
Go ahead,
percentage
Megan.
of the arc length
You're trying to,
to get a percentage of the factor.
you're trying to get a percentage of how much this pipe sees this surface. So if you know the angle, then what do you have? You've got this
View
solution.
factor,
You just divide it by what?
360.
360. So it sees this whole percentage, 53.13. So F1 to 3 is equal to 53.3 degrees over 360 degrees. And what is it, Megan?
0.14.
Very good. 1.4, well,
Well, 0.15 if you don't round.
0.148. Okay? Yes, you did. Good for you. Now, what's left to get?
We can get F1, 4.
We can get F1 to 4, and therefore F1 to 4 is equal to 1 minus 0.5 minus 0.148, or?
0.352.
Correct. So now we have 3 of them.
Can we not?
Go ahead.
Oh, never mind. I was thinking that we could do,
All right, well, let's talk about it for a second. We'll do them in the order I did them in, simply because otherwise I'll get confused trying to find my way around my notes,
okay.
which I do without even getting out of order. So let's take a look at next, surface 2, the reflector. This is what's kind of interesting. We'll leave it at this. All right, here's your reflector, and here's your surface. Now, normally, you'd say, but keep in mind that all radiation which enters the reflector has to enter through what aperture? Through that right there.
Yeah.
So anything that gets into the reflector, in other words, all the radiation which leaves surface 3, which strikes 2, has to go through that aperture. Okay? Right?
So you can model as parallel plates.
So it's parallel plates. So if you model it as parallel plates, and you know everything you need to know, and what is F?
I went haywire, so.
F3 to 2.
0.205.
No.
0.3157.
Okay. Am I saying that right? 3 to 2. Nope.
0.2.
Nope.
I got 0.355.
Nope.
0.325?
Nope.
Oh, I got 0.55, never mind.
Nope. All right, what do I have here? 0.6. If you, okay, let's go back. Hang on. What's X over L?
2.
How do you figure?
1 over 0.5.
Okay, is it that Y over L?
Yeah, that's not one.
No, Y over L is what?
I don't know.
Either of them be X and either be Y.
All right, I have X over L as 1. Opening, the width of the plate is 0.5, the width of the aperture is 0.5, the width of the plate is 0.5. Agreed? Now, what's the Y dimension?
1.
Is it 1? Got to go back to the long plate.
So we have to use the L sub C.
Well, okay, so what would it be?
4.
No. Your Y dimension stretches off for how long? Very, very long. So Y over L is going to equal infinity. All right? And there's a line for that on your table. So you get F F 3 to 2 of about 0.42. And I'm going to call this F3 to 2 prime. Why am I making that distinction?
Because you have to subtract F3 and 1.
Yeah. All right, how do I do that?
You take the reciprocal of 1 to 3
Right.
areas, right?
I know F1 to 3, A1 times F1 to 3 is going to be equal to A3, F3 to 1. Therefore, F3 to 1 is going to be equal to A1 over A3 times F1 to 3. And I can solve for 3 to 1. And it's going to be pretty small. Okay.
0.001.
No, it's like point. It's 0.009. So you've got a decimal place error in there somewhere.
Somehow.
Okay. What's your diameter? Sounds like you're using the wrong
0.01.
diameter. Pardon me?
0.01.
Yeah. Times pi times 0.148 divided by 0.5.
Well, don't you have to times it? Oh, I multiplied by 0.14 twice.
Well, that will do it. All right. So you get f of about f3 to 1 of 0.001. So what do you have to do is, you know that f3 2 prime is going to be equal to the actual f3 to 2 plus the f3 to 1. Agreed? So therefore, the actual f3 to 2 is going to be equal to 3 2 prime minus f3 to 1, and you can come up with f3 to 2. So, and it turns out to be about 0.411. Okay, from there, it's pretty much simplistic, and to get the rest, keep in mind that just as a reminder, F2 sees itself, so you've got to take that into account as well. Yes,
Does the surface 4 see itself too?
the surface 4. Oh, absolutely, but we're not too interested in surface 4, how it sees things. We're more interested in how other things see surface 4.